Yeah, how to measure those fields? You can indicate the results in the scientific language like milliwatts per centimeter square, or you can express it in a much easier value and percent of limit value. So always think about, maybe you are an engineer, you know about physical parameters like milliwatts per centimeter square. Try to explain it to your neighbor or to your partner. Maybe you will overload him if you tell him, yeah, I just measured 0.3 milliwatts per centimeter square at 33 gigahertz. Your partner or your neighbor will not understand you if you tell him, look, I just measured 25% of standard. 100% is your limit, but 25% is still okay. This is much easier to understand. So in Europe, when you look to a bottle of mineral water, you see those indicators like this mineral water contains 12 milligrams per liter magnesium. To be honest, this does not tell anything to me. Okay, I'm not a food scientist. I don't know if this is dangerous or not. I need a much easier indication like, yes, you can use this mineral water for baby food. Okay, so somebody has to translate those measurement results into such an easy indication for general public, and the same applies also to our field strengths. Somebody has to translate field strengths into radiation is okay here or not. Okay, so you can do it or let the instrument do it. Okay, if you are living in a country like Italy and you have there such a flat limit value of 6 volts per meter, or which is equivalent to 10 microwatts per centimeter square, then you can say whatever the transmitting source is, if it is FM radio, mobile phone, or digital radio link, as long as I don't measure more than 6 volts per meter, I'm below limit value and my world is okay. You don't need any knowledge about the frequency because you have a flat frequency range for a flat frequency response of your standard. So here a flat probe can easily give you a judgment. If you are living in a country like myself here in Germany and your limit value is based on the IGNIP limit values, then you can say, okay, if I have 50 volts per meter, I'm not sure if this is dangerous or not. Because if the 50 volts per meter given by a flat probe is at 100 megahertz, this means this is 330% of standard. So this is not healthy. If I have the same 50 volts but at 3 gigahertz, this is only 66% of limit value. So this is still okay. So in Germany, you need knowledge about the frequency if you have a flat probe. Otherwise, you cannot do a judgment because your standard depends on the frequency. A flat probe only helps you if the measured value is below the lowest limit value. Otherwise, somewhere in between, you cannot say it depends on the frequency. But a broadband beamer cannot tell you the frequency. So you are a little bit in trouble. The solution is a so-called shape probe. Shape probe, they have a filter inside, which gives you the possibility that you don't have to worry about the frequency because this is a problem of the shaping filter. Okay? And it gives you a reading directly in percent of standard, so not any longer a value in milliwatts per centimeter square or watts per meter, because the measurement result is now related directly to the standard where the probe is designed for. So look, if you compare the reading of a flat probe and a shape probe, if our transmitter is here at 100 megahertz, the flat probe will give us 0.66 milliwatts per centimeter square. The shape probe will tell you you have a problem. If the transmitter is at 3 gigahertz, the flat probe will still tell us 0.66 milliwatts per centimeter square. I don't know. The shape probe will tell you 66%. So it's okay. For those who are interested, I mentioned it already. We have here the sensor for example, the electric field, and we have the detector. So the RF signal goes down into the detector. The detector is making out of the RF energy a DC voltage, which is later on measured. So the detector is destroying all frequency information. And the frequency response of such a sensor is more or less flat. So this fits perfectly to the flat frequency response of the standard. Inside of a shape probe, we have an additional filter here, a very complicated filter, but this is our problem. And this filter will do a shaping onto the signal so that, for example, lower frequency are suppressed a little bit, medium frequency are let through, and so on before they go to the detector and the frequency information is destroyed. So, and they have a frequency response which is completely inverse to the frequency response to the standard. So if this is your standard, as we've seen it already, this is the response, the frequency response of the shaping filter. By this you get again a flat line, but now in percent of standard. So the shaping filter can help you a lot. And as I mentioned, broadband meters cannot distinguish who it is. So if you connect, for example, a probe from 100 kilohertz up to 6 gigahertz, then the broadband probe will tell you it's 28 volts per meter. It cannot tell you, is it the broadcasting, is it the mobile phone antenna? It has no idea about it. If you want to change the frequency range, you have to connect a different probe. For example, a probe from 40 megahertz up to 40 gigahertz. Then it will sum up all the signals between 40 megahertz up to 40 gigahertz and tells you it's 16 volts per meter. Okay, changing of frequency means changing of the probe. An instrument which can distinguish between different frequency is a selective radiation meter, like the SRM, selective radiation meter, SRM. It can tell you the total amount, for example, if there is an antenna connected between 27 megahertz up to 3 gigahertz, it can give you the total amount between 27 megahertz to 3 gigahertz, which is maybe in our example 3 volts per meter. But it can tell you also FM radio is 128 millivolts, not your problem. TV is 0.5 volts. Mobile radio, I'm standing very close to a mobile phone station, and this is 3.2 volts per meter. So the major impact I get here is from mobile radio. Okay, so the selective radiation meter can distinguish between the different services, can even distinguish between different operators, between different cells, and so on. Okay, so the selective radiation meter is much more, I don't want to say intelligent, but you can get much more information out of it. So why to use still broadband meters? Because they are much more simple to use, they are much lighter, they have a much higher bandwidth with a single probe, and they are also cheaper than a selective radiation meter. The minus is no information regarding frequency or service. You can do it a little bit by shape probes. This can help already a lot. But also shape probes don't give you an indication on the frequency attention. Okay, but it can help you making a judgment. The selective meter can do both. It can do broadband and selective measurement. All frequencies are available regarding frequency or service. It can even do decoding, extrapolation. Yeah, so it's a more how to say, more intelligent instrument to do such kind of measurement, but many times it's also not necessary. Many times you measure very low values, then a broadband meter can be already enough. Here again, a comparison. Here I see 54.9 volts on the broadband meter. Here I also see 54.9 volts per meter on the display of the selective radiation meter. Here, no indication about the frequency. Here I can see clearly I was standing close to a TV tower. So now the question pops up, do I get all the time on both type of meters the same measurement results? Yes, sometimes. Um, if you are exposed to a continuous wave signal in an environment without reflection, you will get on both meters the same result. And this is, for example, inside of a temp cell or broadcasting towers, and there are no buildings around. Then you will get on both equipment the same measurement result. You will not get the same measurement result if you are in an environment where the signal is changing rapidly. And remember, your mobile phone is changing every millisecond its output power. So this is the worst source you can have for comparing instruments. And reflections are also the death of any comparison of test equipment. So even equivalent meters will not give you the same readings because they are different position at different times and so on. It's a little nightmare. Therefore, we have special measurement procedures that you have to do an averaging or a max hold over a certain area so that you get comparable measurement results. The cause for different measurement results are usually the radiation sources or the environment and not the measurement device. Okay, so always think what you are doing. Okay, the measurement device can only show you the result at the following point at the following time. Everything else you have to think about. Okay, so what influences the measurement result? First of all, the transmitter itself, and I mentioned it already, mobile phones and mobile phone towers are the worst source you can have because they are changing rapidly the output signal. TV is also not the best. Analog is nowadays switched off. This is good. Digital is much more stable. 4G, 5G, same rule applies like for GSM. And nowadays with 5G and beamforming antennas, it will be even more difficult because the beam does not point anymore onto you, maybe. So the only source I know which are really very stable are nowadays FM radio stations and digital TV stations. So there you can have very stable propagation and also very homogeneous fields. Okay, here is a place where you can have a very a good environment. Temp cell is for sure the best to compare measurement devices, but nobody has a temp cell, only calibration labs do it. The environment also can have a lot of influence, like reflections, the user itself, he is touching the instrument, other transmitters. Remember, maybe your two test equipments you want to compare have different frequency ranges. Then they also receive different signals. And weather also can have a strong impact, for example, in areas where you have high humidity. That's why many measurement procedures are writing that you have to measure also the humidity, the temperature, and so on to state them also into your measurement report. At the end, we also have the instrument. The setting of the instrument should be comparable. The frequency ranges of the sensor should be equivalent. The size of the sensor couldn't make a difference, and so on. So we have a lot of problems you can face. Finally, it's not impossible to make field strength measurement, okay? And if you want to compare measurement results, for example, free space environment and a tripod can already avoid most of those problems reported here. So, and the uncertainties of the instrument are normally neglectable compared to the problems you can have with your environment. So first think what you're doing, what is the environment here and what kind of signal do I measure? Then you can make a judgment onto the instrument. I mentioned the 6-minute average, and during the first years I was in EMF business, I did also the misinterpretation saying, look, I take a measurement for 6 minutes, I do an averaging over this time, and then everything is fine. So this is wrong. And sorry if I told somebody this wrong believing. What do they say? To be averaged over, attention, any 6-minute period. So you need a sliding averaging interval of 6 minutes and you have to measure it over any time. So this means 24/7. okay? The whole day, the whole night, okay? The whole week, the whole month. And this brings us back to what is the EMF document. The EMF document is not a description how to take measurement, it is a description which biological effects could occur, okay? How you take a measurement, that's a different story. It can give you a guideline, but it does not give you a clear description how to take measurement. Therefore, you have your national measurement descriptions, how to take the measurement, so that not measurement provider A is doing a complete different way of measurement as measurement provider B, and then you are in trouble that those both results don't fit together. So when does averaging 6-minute averaging make sense? So I've taken here some example. In front of an FM or TV broadcasting tower, the output power of our source is nearly constant. So 6-minute averaging means you are wasting more than 5 minutes because nothing will change. Okay, here 6-minute averaging makes absolutely no sense. In front of mobile radios, the output power is fluctuating a lot, and especially with beamforming antennas, we saw now a fluctuation of more than 30 dB. This is more than the factor 1000. Okay, so here an extrapolation can be much more useful. Okay. In a situation where you're standing on a rooftop and you have to maintain antennas and you have the, for example, two-way radios or beamforming antennas standing beside you, sometimes your person monitor will give an alarm and sometimes not. Here it can make sense to use also a 6-minute averaging in parallel so that you can see if the 6-minute average value is getting above the limit curve or not. A short overexposure, also in terms of EMF, is allowed. It's not dangerous. What it means, short or not, is described by EMF inside of this 6-minute sliding interval. So here it can make sense if sometimes your person monitor beeps to get the results back under the limit line by a 6-minute averaging. In industrial applications in low frequency, 6-minute averaging makes absolutely no sense. It's even dangerous because here we are talking about a different biological effect. It's not heating. Heating is not our problem here. Here our effect is induced current, and this starts after a microsecond. Okay, after microseconds enough induced current, you have a problem. 6-minute averaging is absolutely dangerous. In the RF, again, it can make sense. If you have the soldering or welding equipment at very, no, which application run in high frequency, maybe coating equipment, coating of metal, they run sometimes at 2.45 gigahertz. There, again, a 6-minute averaging can make sense. So if the coating just takes a minute and then you have 5 minutes time where there is no exposure, then finally the 6-minute average value is the value which you have to control. Okay, so think about what you are doing and then you know if 6-minute averaging makes sense or not.